All right. Now, oh. And today I have an 8-page worksheet. The copy machine wasn't working, so hence I ended up copying in different places. All right, now there are also review questions. Yeah, but I probably will give it to you towards the end. Now this first question is all about, most of the question is about how you feel, not about whether you are lighter or heavier. I hope you have chosen feels lighter rather than is lighter, I guess. Is this the response? Or you get is lighter? All right. Now the first one, a student at the highest point of her jump, feels weightless. A student in the lift going up at constant speed feels normal or is normal. An astronaut inside an orbiting satellite feels weightless. A student, the moment she presses the down button in the lift, feels lighter. An astronaut inside a faulty satellite plummeting towards the Earth feels weightless. It's no different than free falling. A student, the moment she presses up button in the lift, feels heavier. Lowest point of her jump in a trampoline feels heavier. A bungee jumper falling in the air feels weightless. An astronaut in deep space is weightless. This is the only is one, is weightless. In deep space, when you are in deep space, you are weightless. You don't feel weightless. I mean, you feel weightless, but you are also weightless. If feels weightless is wrong. It should be is weightless. A student at the lowest point of the swing feels heavier. All right? At the lowest point when you're swinging, at the lowest point you feel heavier.
But it's like normally when you're walking on the ground.
No.
Is it relative to being high?
No. When you are swinging, all right, you feel heavier. It's not like walking. All right? Maybe your position is like normal, but at this point, you feel heavier. And can you visualize the swing? And at the bottom of the swing, you go like this. I mean, if it's a big swing, so you feel heavier. Right? So you're not heavier, but you certainly feel heavier. So did I make it as confusing and complicated as possible? Tuba? Yep. Did you find it confusing? Not much? Good. Well, that question is from one of the worksheets. And this question you need to use, there are two methods. Either, careful, this is orbiting a distant star. So I can see you using this formula, T equals square root of, what was that? T equals square root of GM.
Well, yeah, GM, no wait, I have 4 pi squared times the power of 3. Yeah, over GM, alright? Yeah. Over GM.
Alright, so you want to use this. What was the mass of the star? What is this?
No, sir, can you use the T1, T?
Let me finish, all right? So what's the mass of the star? Remember, it's always, next to G, it's always mass of the central object. It's not like any mass. Yes, the mass is provided, but this is the mass of the satellites. We use the mass of the satellite only if the question is about the force acting on the satellite. So this, sorry? Yeah, but in this case, planets are the satellites. In this case, this must be the mass of the star, because the planets are orbiting around the star. Hence, in this scenario, they are the satellites around the star. So this formula is useless since you don't know the mass of the star. So this has to be the star, the mass of the star, and which is not provided. But if you remember, we have said that for two satellites orbiting around the same central object, for two satellites orbiting around the same central object, the ratio of t squared over r cubed is constant. T squared over r cubed is constant, which means for Elif and for Ba, doesn't matter. All right? So, since girls, since the orbital radius of both is provided, since the orbital period of both is provided, and orbital radius, and orbital period of Alif provided, you just need to solve it for B. All right? That's a hard question.
So you know for T, substitute 4 times 10 to the 11. You don't
use the radius of the planet?
Or do you add them?
Oh, use the radius of the
No, the orbital radius, this one.
But you don't add it to
I use the radius of the planet as well. I use the radius of
Do you?
the accident.
Look at the ratios.
Wait, so what do? Do you add the radius to 4?
You don't obviously add them.
things on the wrong.
Yes, careful. Look at the orbital radius and the radius of planet. 10 to the power 6, 10 to the power 11. All right? For this to have any significant effect, you need to have like 6 significant figures first. And second of all is when it says orbital radius, that's it. It's from center to center. Hello, girls. When it says from orbital radius, it's from center to center. From the center of the planet to the center of star. All right? But it says radius, altitude, blah, blah, then you need to be careful. But if it says orbital radius, that's the R. So that is the R. All right? So you don't question whether you should add this or that if it says orbital radius. All right? So this comes here and there. All right? So when you are asked, careful, make this note. When you are asked about two satellites, all right, orbiting around the same planet, always remember this. Always remember this ratio. There is another way to solve that question. You can actually, by using T and R of Alif, you can find the mass of the star. You can find the mass of the star because you know T and R for Alif, right? So you can simply find the mass of the star. The mass of the star is, the mass of the star will be what? T 4 pi squared r cubed divided by g t squared, right? So you find the mass of the star first, and then you put that in here to find the period of the second satellite in 2 steps, or just in one go. Now careful, make note, if you are asked about two satellites, all right, you don't need to go through the long way, you just look at the ratios. Most of the time, if it is about two satellites and a comparison between two satellites, it's this ratio, not the formula. All right, anyway, now our purpose in this quiz is to learn, all right, not to get demotivated. So every time we do a mistake in a quiz, you learn something. But if you don't make any mistakes in the quiz, you don't learn anything. So it's good to make mistakes. Yeah, if the whole thing is wrong, that's a different story. Now, The orbital radius of Mir, the first space station up there in sky, there's only a second one, International Space Station. So Mir Space Station in meters, it's just, girls, you don't read the question. You're asking me which formula should I use. This is only, the altitude is provided, the radius is provided, and you're supposed to find the radius as the radius of Earth, 6,380 plus 380.
I just could just
Yeah,
Dude,
right?
I found it.
And that gives you 47 kilometers, or 4.74 times 10 to the power 6 meters, because the answer was in meters. All right, so you're asking for meters. Now 5 marks, 1, 2, 2. Now the orbital speed, you use this formula, G m over r for orbital radius. All right, and for the orbital period, there are sorry?
Yeah, 6740.
6? Oh, 6. Yeah. And for the orbital period, yes, orbital period, since velocity is 2 pi r over t, you can say t equals 2 pi r over v, or you can use this formula, the confusing one, 4 pi squared r cubed divided by gm, with m being the mass of the Earth, not the mass of the space shuttle. All right? So both should give you the same answer. Then you convert the answer into hours, because this is what the question is asking for. And if your answer is about 1.2, 1.5 hours, it should be all right.
So when I got to the
Look, no, we have to go on, all right? Now, how you have done it, so we'll discuss that later on. Now, that one is about Mercury orbiting around the sun in 88 days. Now, what we are provided is the period, which is 88 days, and the mass of the central object, which is 2 times 10 to the power 30 kilogram. And the question is, what is the radius of Mercury? Now, the radius of Mercury, obviously, is then cube root, remember that one? What was that? 4 gm t squared divided by 4 pi squared. So that's the application of this formula, because mass of the central object, which is the sun, is provided, the period is provided. Make sure you write the period in seconds, not in days. All right? All right, thank you. Now let's move on to electric motors. Now, that was the first. There are some more of them in the secretary. Can you bring them? The main of main. All right. Now, girls, we started talking about electric motors on Thursday. All right. That was the first time we talked about it, and I don't know how much of you will get it. It was a little bit confusing to get it in the first place. So we will go through a quick revision of how an electric motor operates, and then we'll be looking at the last 5 years questions about electric motors. So there in every single question, there are a few questions from DC electric motors. All right? So you can see, if you go through the pages, please go through the worksheet pages, please. And you can see how dense the type of the electric motor questions are. Let's keep going, and you will see in every single year, there are questions. I ordered them according to my lesson plan, but there's pretty much a question. Apart from 2010, I checked only last 7 years. Apart from 2010, there is always an electric motor. So you look at the different designs that they provide you. You look at the different designs they provide you, but it's pretty much the same thing. There is a coil inside, there's a coil inside and inside a magnetic field. All right? So that is the setup that you need to study. Yes, there are other electric motors, all right? But this is the one that you need to study, a coil within the magnetic field. Now, I have some 26 solved questions. 26 solved questions. I will give it to you at the end of the period. It's all about electric motors. All right? So hopefully, by the end of today, and when you study these questions, hopefully tonight, tomorrow we'll be starting something new, 3.3, the particle accelerators will start tomorrow, and hopefully finish by tomorrow. So hopefully by the end of this week, you will have a better understanding of electric motors, about 5-6 marks every year. 5-6 marks every year. So, looking at an electric motor, let's try to, so how did you feel about how the electric motor, do you remember this from Thursday? The electric motor operates, all right? So let's study it again. Let's assume there is a magnetic field in this, let's assume there is magnetic field in this room. All right? Let's say there is magnetic field in this room, which is from this direction. All right? And we have a current carrying wire, positioned, let's say like this. And let's use. Oh no, that's not. So let's use it like this. So let's use different colors for the two ends. All right? Why don't you draw it with me? Let's say this is A, B, C, and D. You see, I use different colors for A, B, and C, D. So it's basically a current carrying wire in a magnetic field. And let's assume the current is running in that direction to start with. All right? So that's the position goes. The magnetic field, all right, and a current carrying wire, and the current at the moment is running in that direction. The current at the moment is running in that direction. This is the direction of current running in that direction. AB, the blue one, and the CD, the red one. The blue one and the red one. All right? Now, at this moment, when the coil is flat, and the plane of the coil is parallel to the magnetic field, not perpendicular to the magnetic field, but parallel to the magnetic field, the plane of the coil is parallel to the magnetic field, all right, at this moment. Let's have a look at the forces acting on each side. Now the force acting on this side, the force acting on this side, on AB, magnetic field, current carrying wire, the current will be upward, am I correct? Right, so the force acting on this side will be upward. The force on AB, right?
Upward as in the direction of the current? Or upward as in,
Force, the slap, the force. No, not out of the page. It's a three-dimensional thing. It's a three-dimensional thing, yes. According to this setup, but try to imagine that as three-dimensional, yes. If it is like that, it's out of the page. But try to visualize it as being flat, not like this, all right? So it will be up, and the force on this one will be the force on CD will be down, right? The force on CD will be down. The force on CD, and that will be down. So, with the forces on AB up and CD down, the coil will start rotating like this, right? And as it rotates, the force on AB stays up. Careful, it won't go like that. As it rotates, the force is not right angles to the coil, but it is at right angles to the side. That's why it ends up being like this. When it turns, it makes a 90-degree turn. You following, girls? Right? So it makes a 90-degree turn. Let's draw it again. When it makes a 90-degree turn, when it makes a 90-degree turn, all right? So let's extend the magnetic field, and let's see what happens when it makes a 90-degree turn. So when it makes a 90-degree turn, the AB will go up. So the AB will go up, all right? And the CD will come down. All right, so the AB go up and CD will come down. So that's like, not the best drawing, but pretty much like vertical, all right? At this moment, the force on AB is still up. No change in current yet. The force on AB is still up. Force on AB. And the force on CD is still down. So the force on AB and the force on CD, up and down. Is it producing any torque? Yes. Can you turn the door like this? Now, by the way, there is an axis along this, and the coil is free to rotate in that direction. But at this moment, the coil will not turn. Are you following? The coil will not turn. At this moment, it won't turn. It won't produce any torque. Like, careful. It was okay when the forces were like this. It was okay. But not anymore. So if you don't do anything drastic, this is what happens. It turns, continues to turn, comes back, and does this, and eventually stop. All right? And if you start your motor like this, it won't turn at all. If you start your motor like this, it will turn and stop here. And if you start your motor at this location, at this position, it won't turn at all. All right? So at this point, you have to do something to make this force from upward to downward, and to make this force from downward to upward. Because if you, as it passes that critical point, if you make this one up to down, see, you can continue turning. So let's concentrate on this one only. Let's concentrate on AB only. If you make this AB, if you make the force on AB from up to down, it will continue turning, right? So it will make another half turn easily. So you make this, so at this point, when the torque is zero, when the force is not producing any torque, the force produces maximum torque now, but the amount of torque it produces decreases as the angle changes, and as the angle is 180, it won't produce any torque. So if you don't do anything drastic, the motor is going to stop. But if you somehow, don't worry about how, but if you somehow change the direction of force from up to down, all right, it will continue its turn. Look, at this moment, it passes that critical point anyway, all right? And after it passes that point, if you make it downward, the force, it will continue making another turn, another half turn, and comes to this point. Again, at this point, the downward force is not helping anymore, so you have to change the direction to up, and makes another half turn, another half turn from up to down, and another half turn, and so on. So if you can manage, so the bottom line is, if you can manage to change the direction of force, when the coil comes to this zero torque moment, all right, if you can manage to change the direction of force, actually reverse the direction of force, you can continue turning. So how can we change the direction of force? If we can change the direction of current. If you can change it. So that's the second part. How we change the direction of current is another story. But what we know is we have to change the direction of current. So at that critical moment, as it passes that critical moment, something has to be done, and this is done by use of a commutator. So you don't need to worry about how a commutator works, but let's have a look at what happens now. At the end of the coil, there are two half rings. Each end of the coil is attached to the ring from inside, not from outside, because the outside is free to rotate. There will be brushes. Again, this end is attached from inside. So the outside is free to rotate, and we have brushes here. We have brushes. Brush 1 and brush 2. And those brushes produce the power that we need. They're connected to the power supply. So you see, this is the positive brush, and this is the negative brush. So at this moment, the AB ring is touching the positive brush, which means the current, it receives current, and current runs and goes like this. All right? Now at this critical point, this is what happens. The brushes are still the same, so I'm going to draw it different here. So there's still the positive brush and the negative brush. At this moment, when it is fully vertical, this is what happens. So as it rotates, the AB ring goes like this. So let's use different colors for AB ring. Let's use blue for AB and red for CD. All right? Now AB makes a quarter of a turn. And we'll go like this. This is AB. This one, AB. All right? And CD, from this point, makes a quarter turn and becomes fully the bottom. And this is CD. All right? Now, none of them is touching any of the brush. So this is the point where they actually lose contact with any of the brush. But thanks to its inertia, it continues to turn. So can you see, AB used to be receiving current from the positive end, right? But can you see as it rotates in that direction, what happens is AB is going to start touching. AB is going to start touching this one. As it rotates just a few angles, AB starts touching this one, and CD will start touching this brush. It used to be AB receiving current, but it is now CD receiving current. That will swap the direction of current, right? And this is what you are looking for, right? You said we need to change the direction of force. Yes. How can we do that? If we can reverse the direction of current. And this is how you do it. The current used to be running from A to B to C to D, right? Back then. But now as we can see, as it passes that, oh goodness me, that critical point, now it's the CD touching the positive one. Can you see that? As CD touches the positive end, it means that becomes positive and that becomes negative, and the current runs from D to C and from B to A. And that's only what happens when it is at this position, when it is at this position, all right, for AB. So it makes another turn, but pretty much the same thing happens every half turn that swaps the direction of current. Yes?
You know the red CD? Is
Yes.
it connected to the red line you drew on?
Yes, yes, that one.
So even when it turns, it's connected to that.
Yes, yes, yes.
The positive, that's right.
Yes, yes, yes. So the coil and the rings move together. The coil, yes, the coil and the half rings go together. The coil and the half rings move together. But the brushes are fixed. Otherwise, you will have, if you attach this wire to the battery and it starts turning, it will be tangled, right? Like if it keeps turning, then that's it. It makes only a couple of turns and that's all gone, tangled. So you have to have a system of producing, giving current to the coil without tangling the wires. And you do that with the brushes. So the brushes are like this. So if the brushes are touching, all right, and they're in contact with the split ring all the time, but constantly jumping from one ring to the other, one ring to the other. So it's not the brushes jumping actually, it's the rings jumping from one to the other. All right, but brushes are constant. Making sense? All right, moving on quickly and looking at some definitions. Now, we already talked about that. Now, the three main parts of a DC motor, can be summarized as, first, regardless of the type of DC motor that you are going to do or you are utilizing, it's going to be, first of all, there is going to be a magnetic field. And because the magnetic field is constant, is not moving, it's fixed, all right? We tend to use the term stator for that. It's not a study design term. You don't have to know. You don't have to know this term. But it is good to know that stator is the producer of the magnetic field. It's pretty much the magnets. The magnets. You have to have a magnetic field. And that is called stator. And then comes the part that rotates, which is called the rotor. All right? Rotor is the part that turns. In our case, it's going to be the coil. You see the past year questions, they don't ask fancy DC motors. They ask only one type, which is this one, or that one, not this one. This is not this one. This is not a study design type of a motor. This is the one, and that is one. But it is good to know that they come in different sizes and shapes.
Would they ask me questions about like how they would operate?
Oh, certainly. There will be questions in a moment. And the third part is the commutator. And a commutator is the split ring commutator, or just the commutator, and the brushes form the mechanical switch. That's a good term. It's the mechanical switch that change the direction of current. Look, we don't care about changing the direction of current, but we care about changing the direction of force. And we achieve that by changing the direction of current. So, the direction of current through the coil every half turn, or twice in each turn, that's the terminology, every half turn, or twice in each turn, so that the coil continues to rotate in the same direction. Now, there is detailed information about a commutator. Let's go through them one by one. A commutator is a mechanical switch that automatically changes the direction of the current flowing through the coil when the torque falls to zero. That's a good term. When the torque falls to zero, because you don't want to change the direction of current now. It is okay now. But you want to change the direction of current now when the torque falls to zero, when the force is unable to produce any torque, any turning effect. And then it changes the direction of current. This is when the plane of the coil is perpendicular to the magnetic field. When this is the case, magnetic field and the coil, then the current changes direction. It consists of a split metal ring, a metal ring that is split. All right, it's a metal ring that is split. Split metal ring, each part of which is connected either end of the coil. So the rings are rotating together with the coil. As the coil rotates, first one ring and then the other make contact with a particular brush. There are two brushes, but if you look at a single brush, it's always only one of the half rings making contact, and then the other, and so on. Conducting contacts called brushes connect the commutator to the DC source. They are called brushes because they brush against the commutator. They brush against the commutator. They're not fixed. They're brushing against the commutator as it turns to maintain contact and conduct current to the coil. The brushes are necessary to stop the connecting wires from becoming tangled. All right? Now, why don't you try to identify parts of the commutator, split metal rings, and the brushes in the following DC motors. I'll help you with the split metal rings. Are these ones, first and second, 1, 2, 1, 2, and these are the brushes. What about the others? What about the others? Why don't you identify the rings and the brushes in the following? So let me just say, so this is ring number 1. This one here. This one. All right, whatever. All right. Split metal ring number 1, and this is split metal ring number 2, and these are the two brushes, brush number 1 and brush number 2. Careful, brushes are fixed. They are not rotating, they're not moving around. The brushes are fixed, but the rings are not rotating. Rings are rotating. In this one, these are the rings, half rings, and where are the brushes? Which one is the brush? The metal things, right? So these are the brushes. So this is the brush now. Brush. And that is the brush. So the two brushes, you see, it's fixed and it produces current to the circuit. Don't worry about the design, it's different. In here, two split rings and the brushes. Two split rings and brushes. Sometimes between the rings there is an insulating material, like plastic. Or it might be empty. But certainly it's a ferromagnetic material in between, either air or something else. And in here, the rings, half rings, and the brushes. Careful, the brushes has to be slightly smaller than the gap between the rings. Does it make sense? The brushes has to be slightly smaller than the gap between the rings. If this is, girls, if this is the gap between the rings, all right, the brushes has to be, the size of the brush has to be slightly smaller than the gap between the rings, so that there is a moment, just a moment, when it is fully vertical, that there is no current. All right, that moment. But it passes that moment very easily, because of its previous motion. But there should be a moment of no current. There should be a moment of no current, because you can't switch the current before you make it zero, right? You have to make it zero and then switch it. Yes?
When is it zero to? Is it like
Now, at this, no. Now, careful. At this moment, torque is the turning effect of a force. Now, force is always there, no problem with that. When they ask you about the force is here. But whether this force produces a torque or not, imagine the door. This is the door, girls, this is the door, all right? And this is the halfway, the hinge. The hinge is not from the end, but from the middle. The hinge, and this is you trying to open the door. Can you open the door like that? Yes, we can. No, yes you can. Now you can. But can you open the door like this? No, you can't. Can you open the door like this? No, you can't. So this is the moment of zero torque. This is the moment of, but careful, there is force, but there is no torque. That's why we change the direction. So the force is never zero on these two, girls. Because regardless of the alignment, these two ends are constantly vertical to the magnetic field. So there is always force. But whether this force produces a torque or not is the question. Now they do, now they don't. That's why we change the direction. But the force is always there. The other two ends, the force depends on the angle, because now the force on this end is zero. The force on this end now is zero. It's not zero now. But because these two are opposing each other, it's just fine. Let's have a look at the questions, girls. Let's move on to the first question. Now this is a 2015 question. You see the half rings. The half rings may be solid, so it doesn't have to be like a ring, but if like it can be like a half cylinder. That's fine. Half cylinder is fine, like this one. You see, a voltage is provided. You can see the brushes, split ring, and the coil. And the coil is named EFGH. The question is, the ammeter shows a current of 4 amp. The ammeter shows a current of 4 amp. We have the size of the coil, and we know how many turns are there, and we know the magnetic field. Question is, with the coil as shown in figure 12, what's the force on the side EF? What's the force on the side EF? Give the magnitude and direction, up, down, left, right. Show you're working out. All right? Now, to find the force, which formula do we need? The formula that we need to use is going to be equal to N times Bill formula. All right? And Bill formula. Nabil. Sorry? I don't know. Read the question. And EF is a square, which means EF is 4 centimeters times 4 times 10 to the power minus 2. Now let me write down what is what. This is the number of turns. This is the magnetic field. This is the current. And this is the length of the wire in meters. This is the length of the wire in meters. 4 centimeters. 4 centimeters, the coil, but it must be in meters. 4 times 10 to the power minus 2. Small force?
I did the exact same thing. It's small force. It's not the power of negative.
So that gives you like 16, 32, 3.2.
3.2 times 10 to the 0 minus 3.2 times 10 to the power negative 3.
That? 3.2 millinewton. All right? That's the magnitude. Confused? What? Now, what about the force? What about the direction of the force? Because the question is asking you the magnitude. Fine. We are good with magnitude. That's it. That's the formula. But what about the direction? Now, north to south. This is the magnetic field. And the current is running, careful, plus. So this is the direction of current. Right? So the magnetic field will be on EF. Magnetic field will be up. All right? The force, is up, yes. The force on EF will be up. Not out of the page or into the page. It's a three-dimensional picture. It's not a diagram, but it's a photo. Yes, it's a photo. So when you have a photo, no into the page, out of the page. All right? You have to either use the terminology provided. And it says up, down, left, right. So it's up. All right? Making sense? Magnetic field, current in EF, and the force is up. So it will make a clockwise turn, right? So it starts turning in clockwise direction, but then swap its direction, blah, blah, blah. That's not the question. The question is the magnitude 3.2 and the direction is up. You got 3 marks. Well done. Moving on. 2012. So we have to speed up, Joe. Speed up. Come on. Speed up. Now, read the question. It says, a small DC electric motor powered a battery through a split ring commutator. The rectangular coil has size kj and lm of length 6 centimeter, lm of 6 centimeters and 3 centimeters. The coil contains 50 turns, all right, an insulated wire, and the magnetic field is provided. B. The question, the current is switched on when the coil is stationary in the position given. Which of the following best describes the motion of the coil when the current is switched on? You may assume that any frictional forces, blah, blah, blah. Look, at this moment, you just need to find the direction of force on one of them, on one of the sides, either JK or LM, not both of them, just one, all right? And then from that force, you find the direction of force either clockwise or in anti-clockwise. You see, there is A and B. This is A and this is B. I think I cut the B part. All right? So there is A. Oh, I cut it. I forgot to get it there. So there is A clockwise and B anti-clockwise. So they even provide you. Now, on JK, girls, can you see as the switch is closed, the current will run in that direction on JK. Let's concentrate on JK. And this is the current, this is the magnetic field, right? Magnetic field, current, and the JK will experience a downward force. A downward force, so the force on JK. And it will rotate in that direction, not A, but B. So the question, that's B, it's only a 1 mark question. Yes?
Why won't it oscillate between A and B?
If it didn't have a commutator, this is what it does. Remember that thing? Things, because it has a commutator, everything is fine. It's going to keep rotating. It's going to keep rotating. It's not going to oscillate. Just careful. If it didn't have a split ring commutator, then it will do this. This is what it means. But it's not going to do that because we have the commutator. All right? Because we have the commutator. But there might be questions where there is no commutator but slip rings. We'll talk about that later on. Then that might be the option, but not for this one. Moving on. It's now asking you the force, and I think it's a 2 mark question. It's a 2 mark question. Come on, quickly move on. So the question is about the application of N times N-Bill formula, which will be 50 turns times magnetic field 0.05. The current is 2. And the length of the wire is 0.06. So that gives you the answer. Don't worry about it. Moving on. Next one. It's a 2006 paper, sample VCAA paper, which means you will have similar questions. Now, it's the same diagram. So they didn't bother drawing a new diagram. It's a new same diagram, 2 questions, 2 marks and 3 marks each. All right? Question. What is the force on the side EH? What is the force on the side EH when the loop is in the position shown in figure 3? Explain your answer. What is EH? What is the force on EH? Now careful, if the force on this one, EF, fine, there's a force because it's perpendicular to the magnetic field. But for this one, what's the force?
No force.
There's no force. All right? Because it's not perpendicular, but it is parallel to the magnetic field. Not perpendicular like this one, but parallel to the magnetic field. So the force on EH is simply 0. The explanation is since it's parallel to the magnetic field, you get 2 easy marks. Since it's parallel to the magnetic field. If the wire and the magnetic field are parallel, or like this or like that, the force simply is 0. All right? So that's 2. Now, explain the role and operation of the commutator in the DC motor shown in figure 3. Now, a DC motor swaps the role and operation. The role and operation. So you need to be careful because it's a 3-mark question. So you just not only talk about what it does, but also how it does it. All right? The role and operation. So the role is to switch the direction of current every half turn or twice in each turn to maintain continuous rotation in the same direction. To swap the direction of current every half turn or twice a turn to maintain or to make sure the coil rotates in the same direction continuously. The coil rotates in the same direction continuously. Or you can also say the swap the direction of current every half turn when the torque acting on the coil falls to zero. And because it says the operation, you probably need to talk about the slip rings, the jumping from one brush to the other one.
So what did you say, the torque acting on the
Coil falls to zero.
So does it say that the commutator changes the direction of current every half turn, or it's talk about its operation?
It's not very clear, but since it's a 3-mark question, I probably will talk about, we have this in your formula sheet anyway, right?
So talk about the brushes as well.
You have this commutator thingy in your formula sheet anyway, so you'll talk about it. You can actually look at the answers for this one and get it and copy that.
You know how we get to take our own cheat sheets
Yes,
as well?
yes.
They also, like there's a data book that's on the VCAA website, so do we get the data book as well as our own
Data book?
cheat sheet?
Yes.
So it's both.
Yes. The formula sheet, you mean?
Yeah, the formula.
Yes, they give you with the exam
So that
the formulas that you need. Yeah, they've got.
I have that.
Yes, but yes, but they don't have this. They don't have this.
Oh, no, they don't have those. Like, obviously, we're going to have to put the abbreviation.
All right, because this is a derived formula. It's not in the program, the VCE program that you have this. It's not in the first-hand formula. It's a second-hand formula. All right. So they only have first-hand formulas. They have this mv squared over r, but they don't have that. So that's why you need to have all that in your formula sheet. Yes. No. Sorry.
Do we have to first show the initial formula?
No. You don't need to do that. You can just say this. Yes.
Can you say it enables the coil to turn in constant motion? Can you say
No. Constant motion, continuous. The coil turns in the same direction, continuously. The coil turns in the same direction to maintain the coil turning in one direction, not doing like this, all right, continuously. Make sure you use 2 things. One direction, not this, and continuous, not constant. Constant is not looking good. All right, what about this one? The motor is operating and the rectangular coil is rotating about the axis of rotation. Mary views the operating from point Q. So this is where Mary is looking at, from Q. Is the direction of rotation clockwise or anti-clockwise? Give reason for your answer. Now this is a question of, this is the direction of current, right? Magnetic field, right? And it will be down. All right?
Oh, yes, yes.
Now it says, Mary is looking at from Q. So looking at from Q, Mary will see the coil rotating like this. Which will be, for Mary, Elif, you are the Mary, what's the direction of this turning? Clockwise or anti-clockwise? You sure? For you, it's turning like this. Anti-clockwise, yes, anti-clockwise. So it's anti-clockwise, yes. And the reason for your answer is you need to talk about the force. You can say the force acting on WX is downward, hence anti-clockwise torque.
Can you say for F, WX at the bottom, instead of saying force on WX? When you're stating,
WX or ZY?
like, no, when you're stating reason,
Yes?
instead of saying force on X or XW,
No, yes?
say F, XW.
Yeah, that would be risky.
Is it enough to say the force acting on WX is downwards?
I think should be all right, I guess. Yeah. I mean, but you can talk about the force on this one and the force on that one, and that, maybe just a few sentences just to be in the safe waters. Just to be in the safe waters. All right, moving on, thank you. Now the next question, they ask you to find the magnitude of the force. It's pretty much the same formula over and over again. You know the number of turns. You know the number of turns. You know the size L and the magnetic field B and the current is 0.5. It's such a waste of question. Next one.
It's always like this.
All right, looking at this one, students build a simple electric motor as shown in figure 18. Figure 18. Yep, pretty much the same. The coil rotating in the magnetic field. Question, at what positions A to D of the rotating coil is the magnetic force on the side XY0? Now careful, which one is XY? Not the one that we care, the other one. The other one. Now,
So can you draw on your exam paper?
yeah, sure. Now, careful. When, at this moment, the force is 0, right?
Yeah.
When the coil is horizontal, with the magnetic field, the force on XY is 0. But what about now? Is it 0 now? On XY. Now, careful, XY. This is XY, girls. Is the force, when the coil is perpendicular to the magnetic field, is the force on XY 0? No, it's not. Now, careful. Now, this wire is perpendicular to the magnetic field, just like this one. This is perpendicular, so is this. All right? So there is a force on XY. So it's only 0, careful, it's only 0 when the coil is parallel, all right, horizontal with the magnetic field, not when the coil is vertical. When the coil is vertical, now careful, when the coil is vertical, there is a force, but it doesn't produce any torquing. There is a force, but it doesn't produce any torquing. So the answer, horizontal with the current in the opposite direction to that shown in figure 18, vertical at all orientations of the coil. No, it's A and B. Because in either case, like this or that, as long as it's horizontal to the coil, to the magnetic field, the force will be 0. Moving on. The student discovered the motor starts moving more easily with the coil in some orientations than in others. So they try to be different in this year. So they realize that in some orientations, now careful, the motor starts moving, now careful, starts moving more easily with the coil in some orientations. In some orientations. Which orientations are these? When the coil is horizontal to the magnetic field. Because at this orientation, which is this one, the torque is maximum. There is no way you can get full mark in this question if you don't use the term torque. All right? So, horizontal alignment. So the key terms here when the coil is horizontal, since torque is maximum. So there is no way you can get full mark if you don't use the term torque in this question, because when the coil is horizontal, the torque is maximum. That's why it's easy to start. All right? You are going to see when you do your the electric motor yourself on Monday, that in some orientations, regardless of how much you push it, it doesn't turn. You have to start when the torque is maximum. Yes, I strongly recommend you to do the rest of the questions in this worksheet, nothing else, the rest of the questions in this worksheet, and as well as these 26 solved questions. And by the end of tonight, by the end of today, you will nail the electric motors. But you have to. Look, you have been wasting your time for so many days. You haven't studied much of physics for the last couple of days, but this is the day that you have to give some time to physics. This night, tonight, you have to fix the electric motors, girls. If you nail it tonight, it's done and over. So we can move on. So make sure you look at the rest of the questions and the 26 questions. See you tomorrow.